Everyone, this is a continuation of the series on vectors. In the last video, we had discussed about the various types of vectors, and in this video, we'll be starting with the addition of vectors. Now, as in case of vectors discussed earlier, in the video we had mentioned that vectors possess both magnitude and direction, and considering that they will be added in a different way, of course, as opposed to the case of just magnitude terms, like in case of scalar quantities. So if you have scalar quantities, they are just added algebraically, but the vector addition is a different ball game altogether. So let's start with the addition of vectors. Now, what do you mean by the term addition of vectors? Obviously, we are adding them. The if we are considering two vectors, first of all, we'll be considering the simple case of two vectors, then we can move over to the multiple ones. So if we are considering two vectors, let us suppose say this is the p vector and this is the q vector, another one over here. Let me take it over here, suppose, right? These are two vectors and they tend to interact with one another. Now, because we know that in case of vectors, we can represent a given vector uh, with the same magnitude and with the same direction anywhere on this page. Just considering that p vector that is over there, the magnitude that we have, that is from one end to the other end, the initial end to the final end, we can take that same magnitude and direction over, let us say, over here. Look, same. So this is the p vector, because it is equal to the above p vector because it has the same magnitude as well as direction. Now the q vector that we have considered over there, that q vector again can be taken. Now let me take this q vector uh, at the ending point of the first p vector. So this q vector that I have taken over here, I can just take the parallel of it and of the same length. I'm taking it nearly parallel over here and the same length. So this now represents the q vector. This q vector and p vector, they constitute a system whose resultant is to be obtained. Now the resultant can be obtained as per the laws of vector addition. So the laws of vector addition, resultant, obviously, as you know, if I'm using the term something called resultant, means it is the result of something. That means it is the result of the addition of vectors, which in turn will obviously give a new vector. The new vector will have the components from the two vectors that have been added. Now, if we are to understand this in a physical world, what we do is, suppose if you have played carom, then when you hit a dot with a striker, right, and so the force that you apply, that being a vector quantity, that force again acts on the other dot that you have struck with the striker, and that dot moves along a certain line. Now the resultant force that we have is the final motion of the striker. Now let me final motion of the dot. Now let me just illustrate as far as I can. So this is supposedly a carom board, and in this what you are doing is you have the striking point over here, the striker is placed over here, right, and in that region what you do is you try to play a cut shot. Now this is a dot, that is the pocket where you want to uh, get this dot right at the center. This dot is to be pocketed at this hole that has been provided over here. So what I do is I apply this force from the striker to this point, right at this point, and it's a cut shot mostly. So in that case what happens is that that dot over there, that is pocketed over here. Now if you see that this was the first vector, force vector, that I have applied, this is the force on the dot that has been pocketed, right? And that force that I have over there, the resultant however is along this direction. The resultant is along this direction that I have just drawn. The figure, although looking clumsy, I can draw it once again over here. This was the striker, this was the dot, force from the striker till the dot. The dot moves in this direction and is pocketed at this point, and the resultant, I can say the final is the final line of action that takes place is along this line that I draw right now. So this is the resultant force, which is a combination of both those forces, the initial and the final force. Now if both the vectors, that is the initial, this one, and the final, if they are acting simultaneously as well, this was the case of a carom example, but if in any other case I have two objects to be moving along two lines like this that I'm drawing right now, those two objects may strike a given object and the resultant motion, this is a common thing that you might have experienced in case of uh, uh, I can take many examples where I can say that this happens in case of even in snooker, okay, 8-ball pool. These kind of things happen where the two dots merge to one point and they strike another ball, and the other ball moves along this path. So this was the initial path of the two balls, and now the third ball is moving along this direction. So these are some of the examples. So that final motion along that line, that is what the resultant case is all about. So you have two vectors or more vectors. Now as of now we are dealing with two vectors problem. So in case of two vectors, we have their resultant, which is just the addition of two vectors. The addition, mind you, is not just an algebraic addition. The addition is a vectorial addition, and a vectorial addition follows certain law. So we have the laws of vector addition. Now, what are the laws of vector addition? Now, as per a law, that is the first of the laws that we can consider is this is for usually for two vector problem. We can extend this law for multiple vectors as well, but as of now initially we are taking two vectors into consideration, just like in case of P and Q. So this law is what we call as the triangle law of vector addition. Now, what is this triangle law? Now the triangle law, we'll be first discussing the statement, then the proof of it. That a triangle law states that if two vectors are represented both in magnitude and direction by the two sides of a triangle, just as in the figure that I have drawn, this figure that I have over here, if two vectors, that is P in this case and Q, they are represented by the two adjacent sides of a triangle both in magnitude and direction, they have to be represented by both magnitude and direction, then the third, and they are taken in the same sense. Now what do you mean by that? By meaning of same sense being that the the termination point of one of the vectors is the initiation point of the second vector. Means they are taken, the tail of one of the vectors is the starting point of the other vector. So we have the two vectors taken in the same sense, representing or represented by the two adjacent sides of a triangle. Then the third closing side taken in the opposite sense. Now this is in the opposite sense, and this gives the resultant. So this is the R vector, which is the resultant, and it is taken in the opposite sense. As you can see, the arrows were moving counterclockwise, while this resultant has been taken in the clockwise sense. So now we have the resultant R is equal to P vector plus Q vector. Now, although it seems like algebraic addition, but those arrows that are above those letters, they have a bigger picture than what it looks like. Now, in order to obtain the exact magnitude of R, we have to follow the geometrical interpretation of it. So what I must do is that I must know the angle that is between the two vectors which are interacting. So P and Q. Now the angle between the vectors is the angle between the two arrowheads. So in this case, this may be considered as the angle, that is theta. In that case, I will be drawing it once again. So this is P, suppose, and this is Q, and this extension is giving the angle between those two vectors, between those two arrows. P terminates at this point. Let me take that. Let me name those points. So this is the initiating point. Let us say this is some point A. This is some point B, which is the termination point. So AB is the vector P, and this is the C. So BC is the vector Q. So AC, as per the law, gives the resultant vector, that is R vector. Let us say that this R vector is making an angle alpha with respect to the P vector. Now what we do is we drop a perpendicular from the point C on AB extended, that is the P vector extended, and we name it, suppose, as S. Okay, PQRS. So this is the Q vector once again, right? And we have the P vector, so the extension of the P vector, the perpendicular dropped from the point C over there. So CS is the perpendicular to the line of AB, or the P vector. So as per the Pythagoras theorem, we have the magnitude of R as, or the square of the magnitude of R as the square of the sides AS plus the square of the side CS. Now AS obviously comprises of P, the magnitude P, and, or I can write it as the length AB plus BS squared plus CS squared. Now if you observe this triangle BCS, in that we have sine theta to be equal to perpendicular divided by hypotenuse. So perpendicular being CS divided by the hypotenuse in that triangle is BC. So what we have is CS is equal to BC sine theta. Now BC is obviously the magnitude of the vector Q, so I can write this as Q sine theta. Similarly, if you take the consideration of the cosine of the angle theta, and cosine will be equal to the base by hypotenuse, which is equal to BS divided by BC. So there again we have BS to be equal to BC cosine of theta or cos theta, and BC is obviously, as we know, it is Q cos theta. Using these values in this above expression over here, what we find is that R squared is equal to AB, which is the P vector, but we are concerned about the magnitude over here. So P, the magnitude of P, plus BS. Now what is BS? BS is obviously Q cos theta. So Q, the magnitude of Q times of cos theta, squared entirely, plus the CS term, that is Q sine theta squared. So what we have over here is P squared. We can get rid of the vector and the modulus notation now. P squared plus Q squared cos squared theta plus 2PQ cos theta plus Q square sine square theta. Now if you know trigonometry, then Q square cos square theta added to Q square sine square theta, this entire term just gives me Q square, because Q square can be taken common. Sine square theta plus cos square theta is 1. So I have P square plus Q square plus 2PQ cos theta. This is the value of R mod squared. So the value of just R mod is the complete root of this entire term that is there. So R is equal to P square Q square P square plus Q square plus 2PQ cos theta, all under root. So this is the expression for magnitude, but R is a vector quantity, so we need to know the direction as well. Now in case of direction, what we have is that R is directed at an angle alpha with respect to the A vector. So we can consider the triangle, another triangle, that is ACS, that is this entire triangle ACS. So in that triangle, what we have is tan alpha is equal to the perpendicular divided by the base. So the perpendicular is CS divided by the base being AS. Obviously AS is something which is consisting of two length, that is AB plus BS. So I have tan alpha to be equal to CS. Now we have obtained CS, that is equal to Q sine theta divided by we have AB to be equal to just P, while BS to be equal to Q cos theta. Now with this entire term over there, we have the value of alpha as tan inverse of Q sine theta divided by P plus Q cos theta. Now if you just take a look at it, I can write it once again over here. We were cramped for space at that point. So at the top I'm writing this again. So alpha is equal to tan inverse of Q sine theta divided by P plus Q cos theta. Now if you observe this closely, you can remember it. My trick to remember this entire thing is that you can see that this is a tan term. This is a tan term, right? And in that tan term, you have another tan term, tan inverse of a tan, because this is sine and this is divided by cosine. So the sine term by cosine term, and it is for the same thing, that is q. So q sine theta by q cos theta. Had it been only q sine theta by q cos theta, we would have obtained tan theta, but that is not the case. We have tan of alpha. So obviously there has to be some change apart from q sine theta by q cos theta. The change is the extra p, additional p. What is that p? P is that side which is with which the resultant makes an angle alpha. So this angle that is alpha, that is the alpha that is the resultant makes with this side, that is P. So that side with which the angle is made by the resultant, that stays alone at the denominator, while the sine and the cosine terms are adjusted according to the tan term. But that would have been tan theta, but with this p involved, that is tan alpha. So it's easier to remember that way. That is how I have remembered it. Right. So this is one of the methods of addition of vectors. The other method, that is the parallelogram law of vector addition, that involves the same procedure, almost the same procedure, but we obviously consider it in a different manner. So let's just quickly take a look at the parallelogram law. Now, the parallelogram law, which is the second form, I'll be taking the next page. So the parallelogram law of addition of vectors. Now in this case, again, it is the addition of two vectors, and obviously the law is just a different approach to it. The resultant will obviously have the same value for the addition of two vectors. If two vectors are having an angle of theta between them, then the resultant will obviously have the magnitude as we had obtained previously, that is p square q square plus 2pq cos theta. And obviously the direction, if it is making an angle alpha with respect to the p vector, the direction will be as that was obtained, will be the same as that was obtained in the previous occasion. So just the interpretation is a bit different, and that is why we have a different law for it. The proof, however, will be almost the same, in the same manner. So what we have over here is, that's the wrong way to do it actually. The vector is initiating, suppose, from a point A and terminating at a point B. So let this be equal to the q vector. And we have another vector, that is the p vector, which is initiating from the point A to and terminating, suppose, at the point C. Right. And this is what we call as the p vector. So this is AC is the p vector, while AB is the q vector, and the angle between them is directly, as we can see over here, the heads are directly can be pointed out. So the angle is theta in this case. Now these vectors which initiate from a common point, as I said, there are many types of vectors. We just discussed a few of them in our previous video. These type of vectors are called co-initial vectors. So these are co-initial vectors which initiate from a common point. Here they are initiating from a common point A, right? So if we have a set of a pair of co-initiating vectors which are represented both in magnitude and direction by two adjacent sides of a parallelogram, then, as I said, that because equal vectors can be represented by the same magnitude and the same direction, so AC can be represented along the line BD, suppose BD. B. Let me write that over there. You can adjust for yourself. So this is BD, which is having the same magnitude as AC and the same direction as well. Now again, AB vector, which gives this Q vector, that can be represented by CD. So this is again the Q vector because of the same magnitude and direction, and this BD is again the P vector. The original vectors were obviously AC, that is P vector, and AB, that is Q vector, but the equal vectors that have been considered, and that is why this is a parallelogram where the opposite sides are parallel and equal in length. So as per this law, we have the resultant to be represented by one of these diagonals. In this case, the diagonal is AD. So R vector is the resultant, that is R vector is equal to P vector plus Q vector. It is the resultant, and that resultant is equal to the diagonal in this case of the parallelogram. Now you have a hint of triangle law in this as well. Now in triangle law, what we had is that AC, in this case, considering this diagram, this picture, AC is the vector P, C is the terminating point of the first vector, and from that point C here, although they were co-initial, that is AB was the Q vector, but I can consider Q vector, considering the case of parallelogram, I can consider the Q vector to be along CD as well, because it maintains its magnitude and direction. So because CD is initiating from the point C, which is the ending point of ending point of the vector P, so in this case we have a hidden triangle law over there as well. So the parallelogram law is almost equal to the triangle law, because if you see that this P vector, if extended, the Q vector is over here, so the angle, again this angle being theta, this angle will also be theta, corresponding angles that we have over there. And the angle made by the resultant is obviously alpha with respect to the P vector, which is the same as we had taken on the previous occasion while deriving the triangle law. So what this tells us, the parallelogram law? The parallelogram law just states, it's a different way of interpretation for the addition of two vectors, that here we have two co-initial vectors represented by both magnitude and direction by the two adjacent sides of a parallelogram, where the resultant is represented by the diagonal. So here the diagonal is along AD that has been considered. Fine. So you can prove it in the same way as we had done in the case of triangle law, that we drop a perpendicular from the point D. Let us say this is the point S, and similarly, exactly in the same manner, we will be obtaining the value of R as P square Q square plus 2PQ. The angle between them is cos theta. So this is the magnitude of the resultant. You can give it a shot if you want to. It will be helpful in understanding the topic by yourself. So you can try this once again. I'm not writing it once again because the derivation, you can just go back by a few minutes in this video and you can see for yourself the derivation part of it. And obviously you have the angle alpha that the resultant makes with the P vector in this case, as well as on the previous occasion. We have alpha is equal to tan inverse of what is that? That is Q sine theta divided by the P stays alone, again Q cos theta. So sine theta by cos theta should be tan theta, but this is tan alpha, so the P term in extra. That's an easier way to remember it as far as I see it. So this is the entire thing about vector addition. we have considered, as of now, we have considered two vectors. In the next video, we'll be discussing a few more aspects of vector addition. We'll be considering the case of addition of more than two vectors, the parallelogram law that is involved in that. And also the various conditions which come up with the addition of vectors, but that is in the next video. Till then, thank you.